All right, so in the journey of going through the urinary system, I want to zoom out a little bit and talk a big overview of how it does the function of filtering our blood and what that actually means. So we're going to look at the functional unit of the kidney, which is the nephron, and some of the major things that it does as it filters blood for us. So what does that mean? Basically, we're going to give the kidney a sample of our blood, and then it's going to put that sample on, I like to think of it like a conveyor belt. And as it travels along that conveyor belt, if it stays on there, it's going to end up in a urinary bladder and then be excreted as waste at the end of the urinary tract into hopefully the toilet. But if it is something that we want to keep, we can pull it back off that conveyor belt. Or if there's something that didn't make it onto the sample that we want to get rid of, we can toss it onto that conveyor belt. So let's talk about that and how we do it. So starting with the nephron. The nephron, as I mentioned, is the functional unit. And so with that nephron, you're going to have a ball-like structure that's going to catch your sample. You're going to have a tube that twists and turns near it. Then you're going to have part that goes down, part that comes back up, do some more twisting and turning, and then an area that's going to collect all of that. So with our nephron, the place where we're getting our sample is going to be called our renal corpuscle. And it's going to include the space that catches the sample, but also the structure the sample comes from. And so for that, I'm just it's really bad art, but we're going to draw it kind of like a box. And that box is going to have blood vessel that comes in and a blood vessel that goes out. And the one that goes out is actually skinnier than the one that comes in. And if you wanted to give you a sample, we're going to put holes in it. So that way you can have some of that sample get through and collected into this ball-like structure. This right here is our glomerulus. It's a fenestrated capillary. That's what the holes are. They're fenestrae. So we have our glomerulus. And so this capsule that surrounds the glomerulus is our glomerular capsule. What you have going in is the sample, or is the blood that you're going to sample from. And so that is going to come in through an afferent arteriole. An afferent arteriole, just telling you know that it's afferent, is going into something. We've seen that before if you've been studying along some other systems where you have stuff going in, like the nervous system. The afferent neuron is the sensory one. It goes into the central nervous system. And so if you have something going in, the one coming out is going to have the word efferent. Now let's break down the arteriole. Arteriole is the small vessel that leads you to a capillary. We already talked about this. The glomerulus is the capillary. It's fenestrated capillary. Here we have efferent. It's still an arteriole. Why? Because it is also still going to take you to a capillary. So the efferent arteriole is going to take you to capillaries that we're going to put right around our nephron. These are going to be our peritubular capillaries. You still have a more twisty-turny look than this, but I at least wanted to show them next to each other in a way that didn't overlap. But in real life, they twist and turn over each other. And also in real life, this folds back this way. But we're going to try to keep it nice and neat here. All right, so we started labeling some parts of our nephron. We had the renal corpuscle. That's the place where you get the sample, made out of the glomerulus and the glomerular capsule. Then we have the nephron tubules, which is this part over here. With the nephron tubules, you'll have the proximal convoluted tubule. We'll abbreviate that PCT. Well, break that down. Proximal, near, so we're close to the beginning, convoluted, twists and turns, and it's part of the tubules. You'll have this one right here that is a loop, so we're going to call that a nephron loop. And then we have the distal convoluted tubule here, which will lead us to our collecting system, which has tubes of different parts, but that's not the focus on this video. Okay, so let's walk through some more of the fizz. When you are in the glomerulus, you have a high hydrostatic pressure. Okay, what does that mean? It's the pressure based on the container. So all of the stuff that goes in, these molecules are going to collide and bounce into each other. And look, the entrance here is so much bigger than the exit there. So what'll happen is you have a high hydrostatic pressure here, which is going to force fluid out. So we have a high hydrostatic pressure within the glomerulus. So this is going to be I'm going to color code this a little bit here. So the one pushing out, so push out of the glomerulus, is your glomerular hydrostatic pressure. Then you have a container. So you have another space with molecules that will collide and bounce into each other. So it's going to push back. So some molecules get pushed back in, but not as many. And so you're having the push out of the capsule, which will move you back into the glomerulus or into the PCT. And so that's going to be our capsular hydrostatic pressure. And so that's going back that way. And I guess if we're going to draw these to scale, glomerular hydrostatic pressure is much bigger than the pressure that pushes you back in. Then, as you have things leaving, what you're going to do is you're going to change the concentration gradient. If we have a change in concentration gradient, it's going to affect osmosis. So we have an osmotic gradient that also will draw water back in. So I think of hydrostatic pressures as a physical pressure where you're pushing on each other, you're pushing on the molecules. And osmotic pressure is like a drawing pressure. It's going to pull you back in. So you do also have pulling you back in because of the large proteins. Those don't fit through the holes. So pull back into the glomerulus, which is going to be our colloid osmotic pressure. And I guess specifically, it's our glomerular osmotic pressure. So maybe that'll make more sense to you. So we'll do that. Glomerular osmotic pressure. And so when you're mapping all this stuff out, there's about a 10 millimeter of mercury push out over these two. So you're going to have more pushing out than what you have drawing it back in or pushing it back in. And so what you end up doing is making a sample through a process called filtration. And so we call this the net filtration pressure when you add these together. So if you take the glomerular hydrostatic pressure and you subtract the two other forces going the other way. So if we subtract the capsular hydrostatic pressure and the glomerular osmotic pressure, and there are different ways to abbreviate these, that will give you your net filtration pressure, which is usually around 10 millimeters of mercury. And so that right there gets you your filtrate. So you have filtrate here. This is the sample. The process is called filtration. So filtration moving across the glomerulus. So it's size selective. You're not picking stuff out and saying, oh, wait, you I need, you I don't need. What you're doing is you sliding into each other and you're next to a hole and you get pushed out. You get collected by the glomerular capsule as filtrate. Once you go into the tubes, we call you tubular fluid. We're going to adjust that tubular fluid. If there's something in there that we want to keep, we're going to put it back into our blood. Because when you get this sample, you cross a membrane. There's no other membrane from here on out to the exit. You're external. This is outside of your body. And so if you bring it back in, this process is bringing it back in. The first time you brought something into your body, it was absorption. That's what we did at the intestines. Here, when you're bringing it back in, this is a process called reabsorption. So we have reabsorption happening here. So filtration here, probably should write that down. So filtration makes your filtrate. You then go into the proximal convolute tubule. You're called tubular fluid. You pull it out of tubular fluid, you reabsorb it. That's stuff like glucose, amino acids. They're small. They'll fit through those holes, but your body needs them. So you're going to bring them back in. So we're reabsorbing it. However, what if there's something like a toxin or a drug that your body doesn't need? Well, we can go the other direction. We can add it to the tubular fluid in a process called secretion. And we can make these kind of adjustments all along. And especially when you get to the collecting system, you can do that using hormones. Here, some of the stuff is automatic. But when we get to the collecting system, most of your exchange, your reabsorption secretions are done. But we can release hormones to tell it to make some other different adjustments. For example, if you're dehydrated, release ADH and say, hey, open up the holes for water so we can reabsorb some more. So that's kind of the basics of the physiology for what's happening when we're doing filtration. We basically end up with a sample that we made based on size, pushing it through the hole because the hydrostatic pressure, the glomerular hydrostatic pressure is high. And we get a sample, we pull some things back into blood that we want to keep, and we secrete stuff that we don't. And we just make those adjustments and then take it somewhere to store and then eliminate it out the other end. All right, everybody. Thanks for watching.